Good afternoon and happy Friday afternoon to you all. I am Hilal Mardet Kremers and I'm a musculoskeletal epidemiologist at Mayo. And thank you for joining us today for a 1.5-hour workshop on use of AI machine learning methods with tabular data. This workshop is the second of a series of 4 high-level training workshops organized through the Department of Orthopedic Surgery. It's targeted especially for those of you who may not have the time and the resources for a formal training in this area. These workshop series is made possible through the Mayo Clinic Musculoskeletal Research Training Program and the P30 Center for Clinical Research in Arthroplasty, both funded by the NIH. Our goal is to help you improve your basic understanding of these concepts without too much technical jargon, create a safe space to ask questions, and also help you identify opportunities to incorporate such tools into your own research. Our presenter today is Dr. Alex Weston. He's a senior data science analyst in the biostatistics department at Mayo. Alex recently completed his PhD in biomedical engineering through the Mayo Clinic Graduate School, and his specialty is deep learning in radiology. Alex is also a member of our orthopedic surgery AI lab called OSAIL, and he collaborates with a multidisciplinary team of investigators in orthopedic research projects. Without further ado, I will pass the microphone to Alex. Alex, please take it away.
Thank you so much, Hilal. So as Hilal mentioned, the topic of today's workshop is a brief introduction to machine learning for tabular data. This is the second in our workshop series. So Puriya presented about a month ago on an introduction to machine learning. And we have 2 upcoming seminars on machine learning for medical imaging, and finally machine learning for text data or natural language processing. So my understanding is this is going to be publicly available on YouTube. And so I don't think there's anything too shocking in here, but just want to be careful and say that my views are my own and may not necessarily represent Mayo Clinic. And one important note, I've tried to keep the examples I'm going to give today for a general audience. In a few cases, I do include specific examples that are specific to Mayo Clinic, just because I think they're interesting or illustrative. But I'll try to make those clear. And finally, I want to acknowledge our funding sources, particularly through the NIH, that were very generous in allowing this workshop series to happen. Okay, so the aims of today's workshop are threefold. Firstly, we want to introduce some basic concepts and terminology related to machine learning for tabular data. And then I've broken this down sort of with 2 aims. So the first is for data scientists. And by data scientists, I just mean practitioners who are doing machine learning research. I've tried to include resources to learn more and tips and tricks that we've learned that can make machine learning a little bit easier. And so wherever possible, I try to include case studies from our own research, as well as links to other sources or videos or things that you might find educational. And just so you know, I'm happy to share the slides. So if you're interested in the PowerPoint version with all the links, just let me know and I can share that with you. And then secondly, for clinical and basic science researchers, I want to share more about the tools that we use in machine learning and hopefully give you a sense of how to evaluate what makes a good machine learning project and eventually how to lead a machine learning project. And one final note on this, so we really want this to be an interactive session. So feel free to ask questions in the chat at any point. And I think Puriya agreed to keep an eye on any questions that might come up. So the other option is if you want to actually ask a question verbally, there's the option to raise your hand. It's a little icon in the lower right of your screen, and that should pop your video up to the top so that we can see that you want to ask a question. Okay, so I've broken this workshop down into 3 sections. The first is talking about the tabular data itself. And I think this is important to start with because data is really the foundation of machine learning research. If you don't have good data, you're not going to get good results. And so I want to lay that foundation by talking about some of the tabular data sets that we're used to seeing, some guidelines for making sure your data sets are high quality, and then I have an interactive example of actually how we go about cleaning data sets. So part 2, which is the bulk of the presentation, is on machine learning. So I'll talk about various algorithms or models that we use that you might experience in research. And then I'll talk about how we evaluate those models. So loss functions that we use, a few concepts like overfitting or using ensemble models that can really improve your performance. And then last but not least, I have a couple slides at the end on the project lifecycle, how we think about machine learning projects from start to finish. So with that being said, let's get started on part 1, the data sets. So the topic of the presentation is machine learning for tabular data. And so the first thing I want to define is what is tabular data? And so in the simplest sense, I think of tabular data as data that can be represented in a spreadsheet. Another thing I like to call it is clinical data. So this includes things like clinical outcomes, patient surveys, basically anything that you can represent in a spreadsheet form. So we think about this differently than other types of data, such as signals data or imaging data. And so signals data, we basically mean things like EKGs, EEGs or electroencephalograms, accelerometries, voice recordings, other recordings like this. So those signals are also 1D like tabular data is, but they tend to be more sparse. And then the third data type obviously is imaging data. So things like CT scans, MRI scans, pictures, and videos. And so I would say the biggest thing that differentiates tabular data from these other data types is just the density of data. And what I mean by density is, so if you think about comparing an image to a spreadsheet, if you have an image, if you were to change 1 pixel in that image, it might not necessarily have a very big impact on your interpretation of that image. Versus if you have a spreadsheet, if you change something like a patient's weight or their height, that could drastically impact what your interpretation is for that patient. And so that's what we mean by tabular data tends to be much more dense than image data or signals data. And the reason that's important is because it informs a lot of the algorithms that we use on tabular data versus these other types. So there's a few basic requirements or characteristics of tabular data sets. And the first is that these basically comes down to formatting. So when you're formatting, for example, a spreadsheet, each row is going to correspond to 1 observation. And by observation, we mean a patient or a clinical visit or surgery or whatever it is you're measuring. And the other requirement is that all of the observations or all of the rows have to have the same number of variables. So the same number of columns for all of the rows in your spreadsheet. And the caveat to that is missing data. So there's various ways to handle missing data, but commonly you can replace it with an NA or just leave it as a missing value. Or in some cases, you can actually impute those values. And so just a shout out to an interesting resource here, a resource I really like. So Hadley Wickham is a developer for the R programming language. And he calls this characteristics of these tabular data a tidy data set. So if you have a full set of rows and a full set of columns, that's considered a tidy spreadsheet. And it really changed my perspective on how we think about data cleaning. And so I have that link here if anybody's interested. And I also have a link to a shorter version of the article down here below. Okay, so the NIH has actually come out with some guidance on further guidance on the requirements for tabular data for machine learning. And so the first guidance that came out, I think in 2016, is that the data should be fair. And by fair, that is an acronym that stands for findable, accessible, interoperable, and reusable. And so I have a link to the guidance down below. And so there's a number of different characteristics that the NIH has published. I think there's over 100 different rules that they use to help you decide if your data is fair. But for example, 4 of the ones that I pulled out here, so the data has to be findable. So all of your data should have a unique and persistent identifier. This goes back to the concept that each of your observations should be on one row. Your data has to be accessible. So if you're going to share this with other people, there has to be a way for people to access the data and authenticate new users. So for example, making sure people get added to AJRR-Bs, making sure there's a process in place for that. Interoperable, so you have to define the variables in your data sets, and particularly if there's relationships between variables, you have to define what that relationship is. So for example, BMI depends on height and weight. And so, you have to record basically how you're getting that BMI value based on the input variables. And then finally, to make sure your data is reusable, you have to describe it in such a way that people can understand it. Okay, and then the second criteria that NIH updated, I think last year, is their trust criteria. And trust stands for transparency, responsibility, user-focused, sustainability, and technology. And this pertains specifically to data sets that are being shared in public repositories. So things that you're publishing on the internet for other people to use. And I think the best way to illustrate these fair and trustworthy criteria is just to share an example of a data set that does a really good job of meeting these criteria. And so this is actually a data set that's published through the NIH called the Cancer Imaging Archive, or TCIA. And it's a repository of medical images related to cancer imaging. So there's 160 different collections of CT scans, MRI scans, X-rays that correspond to a variety of different cancers. And so I've included a link to that resource as well if anybody's interested in that. Okay, so when we think about acquiring data for developing a machine learning algorithm, there's only 3 ways to get the data. Either you have to record it yourself, you have to download it, or my favorite example is you have to find someone that already has the data sets and partner with them. And actually, I think this third option gets overlooked a lot, but there's a lot of amazing research that's being done here at Mayo. And so when I have a new project, often the first thing I'll do is just ask around to see, is anybody else looking at this problem? Because typically you'll find someone that has a similar interest, and then potentially you could save work for both of you. Okay, so I wanted to include this example of how we record data very briefly. So this is RedCap, which I think is a tool that a lot of people are familiar with, but it's basically a form for inputting data. So rather than just recording things in a spreadsheet, you can create a RedCap for your project, which has very well-defined questions here that data analysts can fill out, which usually makes it a little bit clearer than a spreadsheet. And then finally, the really nice thing about RedCap is that you can export your data set on the back end as a spreadsheet, and it comes out fully formatted in this tidy format, essentially. And so you don't have to do a lot of data cleaning because RedCap does the cleaning for you, which is one of the reasons we really like it. And so like I said, probably most people are familiar with this, but if not, I have a link down below. And there's some resources if you want to learn more. Okay, I'm starting to see questions in the chat. Oh, never mind. Just something else. Okay, so then the next way to get data is to download it. And so most of the data that we use in clinical research comes from the EHR, or the electronic health record. And so this is a vast set of data sets that are already saved in the tabular format. And this is where I'll talk about something that's specific to Mayo Clinic. So Mayo uses Epic as its provider for the electronic health record. And so other hospitals may use different systems, but I think they all are similar, essentially. And my boss, Dr. Ricky Carter, likes to say, if you can see it on the screen in Epic, we can download it, which sounds a little bit like over-promising. But essentially, if it's on the screen, it exists somewhere that we can access it. So I thought I would include just a brief spreadsheet of what the EHR looks like. So most of us are familiar with Epic. So Epic is the front-end interface, we say, to the electronic health record. So it's a menu essentially, and then it pulls and pushes data back and forth to the EHR. And the EHR is just a collection of different databases essentially with different data in them. And so, there's different tables, for example, for demographics. So the surveys that patients fill out while they're sitting in a waiting room, that's one table. There's another table for ICU data. There's another one for radiology images. And all of this basically is saved in different places in the EHR. And so if you're a data scientist or if you have access, essentially, you don't have to go through Epic. You can go through the back end, basically using SQL and download these data sets directly from the EHR. And there's other research tools often that if you're not familiar with SQL that you can use to access this data as well. So I know here at Mayo, we have the Mayo Data Explorer, which is a really nice web interface that you can use to parse through data sets in the EHR. So within the EHR, certain things, so like I said, if you can see it on the screen, it's available in the EHR. But certain things are easy for us to pull and certain things are more difficult for us to pull. And so I include this slide just because it's a very common question that we get when we're starting a new project. And so things that are easy to pull include demographics data, diagnosis codes, procedure codes, and admits and discharges. So a few examples of things that can be a little more difficult. And by difficult, I don't mean impossible. I just mean somewhat more time consuming. But if you think about values that are going to be recorded differently in different places at different times, it's often difficult for us to zero in on that data that we need. And so, for example, sometimes different labs in Florida will record values differently than in Rochester. And so essentially that makes us have to pull the data twice, once in the Florida data set and once in the Rochester data set. And then, sometimes there's different lab protocols that get updated over time. So, they'll be doing recording things a certain way up to, for example, 2016. And then after 2016, they'll record it a different way. Well, again, that means that we have to, first of all, know that difference and then account for that. So it can just be a little bit more time consuming. The other thing we need to watch for is values that are often missing. So patient surveys, unfortunately, are notorious for this, which is that often patients don't provide answers. And so we can expect a high amount of missing data, as well as things that aren't always getting recorded, such as sometimes treatments don't always get recorded. And then finally, values that are highly unstructured. So medications are a great example of unstructured data. So medications are always recorded, but if you think about it, for any given drug, there's a name brand drug as well as many different, other formulations of that drug. And so for any given treatment, sometimes you can have 10 or 15 different medications that are all labeled differently that we might not understand that you have to clean out then. Okay, so I wanted to end this section with an interactive example. And so I want to show an example of a data set that we're using in orthopedics research, which is related to total knee arthroplasty. And so the purpose of this data set is we have a list of characteristics of patients that are undergoing TKA. And we're going to try to predict whether or not they're going to have a complication based off their characteristics. And so just a little background on TKA. So as many of you know, it's a very common elective procedure. Complications for TKA are rare, but they can be significant because, primarily the people that are getting these procedures are elderly. So this is an actual data set, actually, I've taken from one of my projects. So it's completely de-identified. One thing I want to mention, so just for the purposes of this presentation, I've increased the complication rate. So it's actually very, very rare for patients to have a complication from this procedure. But just for this data set, I've enriched it with a few more complications. Okay, so let me switch to my spreadsheet. So I apologize if the text here is a little bit small, but hopefully everybody can see this. So like I said, this is an actual data set that actually Hilal and I are working together on for a project. And so just an example of some of the variables here. So we have the patient's gender. We have the side that's being operated on, left or right. We have their date of surgery. We have their age at the time of surgery. We have their height, weight, the anesthesia time, so the amount of time that they were being operated on, some information on the procedure, whether or not it was minimally invasive or not, the location, and then finally our outcomes. So we have the date of complication and then the complication code. And so these codes, you know, are written as numbers, but this is something that we can go back and look up to see what the actual complication was. So this is just to introduce the data set. So now I'll talk about what we're going to do to clean up this data set. And so a few things that we like to do for cleaning for machine learning. So first of all, we want our data set to be in a spreadsheet. So when we're saving out data, it should be in the CSV format, not Excel. And that's because just Excel, you know, if you're using a programming language like R or Python, you can read CSV formats, but not necessarily Excel formats. So just making sure that, you know, that data set can be read by any programming language. So as I mentioned before, the data set should be tidy. This is an important one. So for a machine learning algorithm, all of our variables need to be encoded as numbers, essentially. So categorical, either zeros or ones, or continuous values. We like to have clean column names. So Pat Johnson on our team actually shared this actual example of a spreadsheet he had where this is one of the column names, which can be a little bit hard for us to understand. So just making sure these are clean, making sure your units are clearly labeled. And then if you have other data that's not in the spreadsheet, making sure that we link to that. And so, you know, this is my like 30-second version of these rules. Actually, there's a really nice article down here that describes in 6 simple steps how to clean your data set. So if that's something that you're interested in, I have the link down below. So if we go back to our interactive example, so this is the data set after cleaning, and I've just highlighted in green some of the changes that we've made. So the first thing that we've done is we created a unique identifier for each of these rows. This is something that was missing in the previous spreadsheet. Instead of recording male or female, we changed these to binary variables. So this is a 1 if the patient is female, a 0 if they're male. And the same thing with the side. So this is 0 if it's left side or 1 if it's a right side. We have a link here. So this is just illustrative, and this is not actually something we would use when we're building our model. But you know, in the case that we had X-rays or MRIs for these patients, it's really helpful to include that basically in the spreadsheet. So we'll just have a link to the server and where the image is stored on the server. BMI, so in the previous example, we saved the height and the weight as separate columns. But in this case, what we really care about is BMI. So we just calculated the BMI, and that lets us get rid of 2 columns in our spreadsheet. So it's a little bit simpler and a little bit cleaner. And then our approach, we filled in the missing values with NAs. And then our complications, we encoded them as 0s and 1s. So hopefully this is just, you know, a brief example of, you know, how we would go about cleaning a spreadsheet like this. Okay. So I'm going to end this section with 2 case studies. And these are examples of how we can get tabular data sets from non-tabular data sources. So this is a really interesting example, I think. So I stole this from one of my coworkers, Dr. Heather Hartway, who works with me in Digital Innovation Lab. And she has a project in dermatology, essentially reading through biopsy reports to extract values from the biopsies. And so if you were to go in Epic, this box at the top shows an example of what these reports look like in Epic. So you can see that they're somewhat structured, but there's a lot of you know, free text here that's a little bit hard to read through, and there's potential for typos and things like this. And so she wrote a Python program essentially that can step through this report and highlight the parts that we care about. So the anatomy or the location of the biopsy is in orange here. The size of the lesion that we're biopsying is in the light blue. and then some information related to the diagnosis. In this case, squamous cell carcinoma is in purple. And so essentially this Python program is stepping through this very disordered free text and filling in a tabular data set with the diagnosis and the anatomy. And so I think this is an interesting case of how we can extract these tabular data. And the final project I want to mention is from my own research in the field of radiomics. And so this is extracting tabular data, particularly texture features from MRI scans. So in this case, our project is with liver cancer, hepatocellular carcinoma. And so I have examples of these MRIs of hepatocellular carcinoma at the top. So we've segmented out different regions. So the green is a segmentation of the liver, and then red is a segmentation of the tumor. And then we're also tracing out the local region in yellow as well. And so using a Python package for radiomics analysis, basically we can feed in this image and it gives us values associated with textures in here. So I have some examples of these features down below. So things like the minimum pixel value, the maximum pixel value, the kurtosis or the distribution of pixels, entropy, energy, things like this. And so basically instead of this large image, we get a very simple list of features that are correlated to things like perfusion or the size of the tumor or other things that we want to study. And so radiomics is a rapidly developing field, but it allows us to treat some of these imaging data as if they were tabular data sets. Okay, so that wraps up section 1. I think this is a good place to pause for questions if anybody has any questions. What if we decide that we need more data? So that happens a lot, actually. Oh, I see. Yeah, so this happens all the time. We start with a set of variables, and then we're doing the analysis, and then we decide that actually there's these other variables that we didn't look at that are going to be really important. And so, this happens all the time. It's something that you need to be a little bit careful. So basically what we would do then is we would download those new variables as a second data set and then merge them in with the first data set. And so that's where it becomes really important to have all of your rows identified, right? Because that way you can link up multiple versions or multiple examples of data sets together. So, for your example, if we needed age, we could go back, we could download all of those patients with their age and then merge that in as a new column in the data.
Okay, I just followed Dr. Ginger's question. For example, when you, in your total HIP study, the worksheet showed the, whatever the factor or parameter you're going to look at, the question is who is going to decide it? From that worksheet, I can tell maybe they're missing one very important element for total HIP is what kind of HIP. There's several different design of the HIP. For example, cemented, compare cementless, the complications are different. So for that, I didn't say that factor is the HIP design is in your the independent variables. So that's kind of Ginger's question. Who do you decide that, okay, I think age is important, or bone density is important, or maybe other disease like diabetes is important factor for your complication. So I just, because this machine learning is very broad, we can have maybe more than 50 parameters we can study at the same time. I thought that's the advantage of machine learning. But yeah, if you use people, you cannot probably do this because you cannot study 50 variables, independent variables, for just the outcome measure is a complication.
Yeah, so that's a really good point. Yeah, so first of all, the original version of this spreadsheet had 180 different variables, right? So
Oh,
I've
okay.
simplified this quite a bit.
Right. Okay.
For our,
Okay. That's
presentation. But that's a really good point, which is that, in a lot of cases, the reason we use machine learning is because we don't know exactly which variables are going to be important. And so you're right, it is really common that we'll include more than we think is necessary, right? All of the variables that we can have, and then trust that the machine learning algorithm will be able to pick the ones that are important. And actually, I have a few examples of that later in the presentation.
great. Fair enough.
Yeah, so I think, yep, I see your question in the chat. So I think it would be better to start with a larger data set with all of the variables that might have any chance of being important, and then reduce the size as we need. Who is the surgeon? I don't know the answer to that. I think it was multiple surgeons in this registry.
Yeah, actually, what I mean by that is that that's an important variable as well as who the surgeon is.
Yeah, for sure. Yep, so that was something that, for example, was recorded in the original version of this. Can you identify which features are important after training? Yes, absolutely, you can do that. Yep, and I do have a couple slides on that later in the presentation. So that brings us, I think, to what's the interesting part, which is the machine learning. So I think this is a slide that I stole from Puria in his first presentation, but basically defining, there's a lot of terms that get thrown around related to AI, and so just defining the terms. So AI, by AI, we mean any technique which enables computers to mimic human behavior. So training computers to do things that traditionally humans have been really good at. So machine learning is a subset of AI, which is algorithms that are able to learn from the data without being explicitly programmed. So like we were just talking about, not telling the algorithm exactly which variables are important, but having the algorithm learn those variables itself by giving it examples. And then finally, deep learning is a term that you hear obviously quite a bit. This is a subset of machine learning. Essentially, deep learning is a specific algorithm or a specific model that fits within this umbrella of machine learning. And so for today's presentation, we're mostly going to be talking about this green box. I have examples of machine learning algorithms. I do talk a little bit about deep learning. Okay, so the first distinction that we need to make is between supervised machine learning and unsupervised machine learning. And so supervised machine learning, we mean when we use human-labeled data to train a model. So for an example, if you have a data set, you would ask an image analyst or someone like myself to go through and label all of your examples. So like in the previous, we label if there's an outcome or no outcome. And then we ask the algorithm to learn the relationship in the data such that it can predict what that outcome is going to be. So the second type is unsupervised machine learning, and this is where you don't provide any labeled data to the algorithm. So essentially you provide just unlabeled data and you ask the algorithm to find naturally occurring patterns in the data. Okay, so I think that when we give these machine learning presentations, we make sort of a conceptual leap. So we start off by talking about Excel spreadsheets and things that are very intuitive, and then we end up talking about dots on a screen, which I think can be not very intuitive. And so I want to include this example just so that we can start to think about spreadsheets in dot format, so to speak. So think about spreadsheets in a hyperdimensional 3D or 4-dimensional space. And so this is a data set that I stole from one of my coworkers, Zach. And it's from a project looking at pulmonary function testing. So patients breathe into this device and it records things like their forced expiratory volume or how much air is contained in their lungs, their rate of exhale, things like that. And so this gives us a spreadsheet of data. And essentially what Zach's done here is he's plotted the relationship between all of these variables in the data set. So this is a supervised example. So he's gone through and labeled whether or not the patient has a defect in red versus, green, blue, or other colors, and then plotted that relationship for all of the variables. And so what quickly jumps out at you on this graph, so first of all, some of these variables don't seem to have much of a relationship, right? So many of the variables in the second row, have a lot of overlap between these different groups. But there are a number of variables here that look like they're clustering into different groups. And so if we were to plot these variables, right, on a 2D graph, we would get a scatter plot, essentially like the slide I just showed. And so what machine learning is doing is it's reading through all of these examples, and it's finding these relationships in the data, and it's pulling out the variables that are important, and it's ignoring the things that aren't. So the next thing I want to talk about is what we mean by learning when we say machine learning. So a machine learning model, when we say model, basically a model is just an equation. So a model is a relationship in the data. And so when you start with a machine learning algorithm, you initialize it with a random value, essentially. So you don't know anything about this model to start with, you just give it a random input. And so this is an example of this, right? Our data sets are this, the white dots here, and our model is this line, which doesn't tell us anything at all about this slope. So the second step in learning is that you calculate the difference between the data points and your model. And this is what we mean by the loss function. So in this example, we're calculating the distance between our white dots and the predictions that are generated by our orange line or our equation here. And this gives us some loss value down here, which in this case is pretty high because our model's doing a poor job. So the second step, and this really is where it comes down to the learning, is that we update our model to, based on the loss function, to try to capture features in the data. So we're going to update our model parameters here. So my M1 now turned into M2, and my B1 turned into B2, and the model's doing a little bit better job of calculating the slope here, and so our loss has gone down. And then we repeat this process. So we give it another random iteration, and then we recalculate the loss function, and then we update it again and calculate the loss again and go back and forth. And so over time, we say that this equation is learning, quote unquote, this relationship within the data. So this process of learning is captured by a loss curve, which is a graph that you often see in papers. And so over time, we would expect that our loss is going to decrease over the number of iterations. And another common term that you'll see here instead of iterations is epochs. And an epoch is basically when the model has seen the entire data set once. So when your model has seen every single training example, that's one epoch. And then for the second epoch, it sees each example 2 times, and et cetera. So of course, it'd be great if we can get these really smooth loss curves, but that's not always what we get to see. And so I've included this example of a loss curve from one of the projects I'm working on. And you can see that it is a random process. So sometimes you'll get peaks or disturbances in your learning rates. But over time, hopefully at the end here, you converge on a stable value. And this means that your machine learning has basically learned everything it can about the data. Okay, so next I want to talk about some of the different families of machine learning models. And so I'm really going to talk about 4 today for the workshop. And so within the class of supervised models, I want to talk about logistic regression, tree-based models, and neural networks. And then I have an example of unsupervised learning as well, which is k-means clustering. Okay, so the first one I want to talk about is logistic regression, or a similar model is support vector machines, or SVMs. And this actually is very similar to the example that I just showed with the dots and the orange line. And so these algorithms, logistic regression algorithms, are trying to find a decision boundary, or essentially a line or a plane that optimally separates 2 groups within the data. So with this little schematic here, we have our blue group and our red group, and the logistic regression is trying to draw this green line that separates those 2 groups as best as we can. Okay, so the first example that I showed actually is an example of linear regression. which I think is something all of us are familiar with. But this is good for when you're trying to predict a continuous output. So when you're trying to predict an actual value, you would use linear regression. But in a lot of cases, we want to use machine learning for classification. And so we basically have to turn this linear regression algorithm into a classifier. And so the way we do this is with an activation function. So an activation function is a nonlinear function that basically forces your output to be either 0 or 1. And so in this case, 1 would be a positive prediction and 0 would be a negative prediction. And so wherever our prediction, falls within this line, it's going to be forced to a classification threshold. Okay, so the second algorithm I want to talk about, or the second model, is a decision tree. And decision trees, I think, are actually one that's very intuitive to a lot of us because they're ones that are commonly used in clinical practice. And so I actually have an example here that I'm working on with Heather related to penicillin allergy. And so an example of a decision tree, we have different variables or different characteristics. So whether or not the patient had the symptom of anaphylaxis or 2 or more symptoms, and whether or not you answer yes or no makes it more or less likely that you are allergic to penicillin. And so this is a great example that's rules-based, but of course with machine learning, we want to learn this ourselves. And so the machine learning can learn, first of all, which variables are important, and then the order of variables that contribute to these different decisions. So there's a couple modifications to decision trees that make them much, much more accurate for machine learning research. And so, again, these are things you're commonly going to see, but random forests, which is essentially when you take many different trees, usually 100 or 1,000 decision trees, and train them independently, and then combine all of those trees into an ensemble model. Another variation is a boosted tree. And with boosted trees, you increase the loss function over the number of epochs, essentially increasing the loss function over time. And so this forces the algorithm to correct wrong predictions, essentially. So over time, you increase the penalty associated with wrong predictions, and this makes your model more accurate. And then there's a specific example of a boosted tree called XGBoost, which is available on GitHub or other sources that's extremely accurate. So when you see these data science competitions in Kaggle or other places, typically this XGBoost is one of the best models. Okay, so the final algorithm or supervised algorithm I want to talk about is a neural network. And this is probably the most famous or potentially the most infamous of the machine learning models that we see. And so if we go back to our very first logistic regression example, essentially you could consider this simple equation or this simple model as one unit or one node in a much larger algorithm. So we have our single logistic regression model here, but we can chain these together. So in this case, the output of our first logistic regression feeds in as the input to subsequent regression equations. And so this forms a quote unquote neural network or a network of these equations. And the reason this is so powerful is because it can capture very, very complex relationships in our data. It's not just a linear equation anymore. Now you can capture very, very complex features. And actually, the reason these are called neural networks, which I think is very interesting, is these equations where you take multiple inputs to generate one output. In a way, they mimic what the neurons are doing in our brains, right? So a neuron takes inputs from other neurons and creates a single action potential that can be thought of as our prediction. And so it's not a perfect example, but that's sort of what inspired these types of networks. And what we mean by deep learning, essentially these models can get very, very complex. And so this is a screenshot of a deep learning model called AlexNet. No relation, but this is one of the very first deep learning models that was successful back in 2016 that got first place in one of these data science competitions. And you can see how complicated this model is with all of the weights and connections. And so I consider that constructing these architectures or developing these models, that's often the really fun part of our jobs in deep learning, is coming up with these interesting configurations of neurons. Okay, so I think deep learning can have somewhat of a reputation as being black box, which is actually a term I don't like very much, but this is a word that gets used. And so why do we consider deep learning black box? Well, I think that it's only black box because it's a complicated model, right? So the basic unit of a deep neural network is this very, very simple logistic regression function, right? So we understand all of the parameters and all of the weights and all the math, basically, that's included in this algorithm. It's just that there are so many hundreds of thousands of connections that we can't possibly visualize all those relationships. And so we have to use other tools that I'll show later to try to understand what our deep learning model is, quote unquote, seeing. But that's not to say that it's black box, because we actually understand all of the math that's behind it. It's just that we can't visualize it because it's so complex, essentially. Okay, so the final example I want to show is an example of unsupervised learning. And so this is one, again, where we don't have labeled data to feed the algorithm. And so this is an example of k-means clustering. So essentially, you tell the model, you don't tell the model what the labels are, you just tell it how many clusters you expect to see. And then the model basically finds the location of each cluster by minimizing the distance between each point and its given cluster. So for this example, you could see the cluster centers, conceptual example, it centers on basically the midpoint of all of these different clusters. Okay, so that sort of wraps up my section on the different algorithms or the different models that we use. So next I want to talk about how we select the right model for the job. And in many cases, as you would expect, there's many different models or many different algorithms that are going to be appropriate. And so how do we choose the very best one? Okay, so I have a little quiz question for us here. So going back to the spreadsheet I shared, predicting complications based on knee replacement procedures, my quiz for all of you is, which of the 4 algorithms I just talked about would you think to try first? Logistic regression, random forests, neural networks, or k-means clustering? Feel free to put your guesses in the chat, or I guess if you're brave, you can share. Oh, we have one guess. Logistic regression. K-means, 2 for logistic regression. Oh, Barty is hedging his bets. Logistic regression, but second would be random forest.
No, I meant my go-to model for starting would be a simple model, so such as logistic regression, but probably from these choices, random forest would work best for the problem. Okay. My guess.
Yeah, so I would say the right answer is that there is no right answer. I think any of these algorithms potentially could do a really good job. So I actually, me personally, I agree with Bardia that I think that random forest would do a really nice job here because it's already sort of set up like a decision tree, right? So you can imagine that if the patient is older, you know, certain variables might be important. You know, if they're older, their BMI may make a difference. If they're younger, potentially it doesn't, right? So my bias would be towards using something like a random forest, but you know, I think any of these algorithms could do a really good job. K-means clustering is an interesting one. So in this case, we have a labeled data set. So you could use K-means clustering for this, but K-means clustering is really popular when you don't have labels. But in this case, we know what the complications are. So I think we can use these other ones. Yeah, Poria, exactly right. Random forests are a combination of tree models. Yep, neural nets. Yeah, so I think, so I'll talk about this a little bit later. So neural nets for sure will work. Neural nets tend to do better on really, really complicated problems. So because they're so complex with many layers, you know, neural nets really like examples where you have hundreds of variables. And so in this case, I mean, I think neural nets will do a nice job. I think they're going to be a little bit more overpowered. Yeah, risk of overfitting, Tuggy, exactly. Yeah, Poria, that's been my experience. So neural nets sometimes do a good job and sometimes they drastically overfit. Okay, I'm going to keep going here, but if anybody else, oh, we have a question. Is there any augmentation such as in computer vision? That is a great question. So yes and no. So augmentation, so first of all, for those who don't know, augmentation is a way of basically injecting random noise into your measurement. So, you know, you can basically add a small random value to your variables. And this makes your model, it helps with overfitting a little bit. And it can also trick your model into thinking you have a larger data set than you do. And so I think augmentation is really, really important in medical imaging because CT scans and MRI scans already are noisy, right? Like if you look at a CT scan, you already see random noise on the screen. And so it makes sense that you would add some random noise to that measurement. I don't know that that's always necessarily true with tabular data. And in some cases, it can be a little bit weird to inject random noise into your measurement. So like, for example, with BMI, you wouldn't want to add so much noise that your BMI value doesn't make sense anymore, right? You don't want to push it over something that's physiologically relevant. And so I think that there's still appropriate times to use augmentation, but it's not always a given like it would be in medical imaging research. I don't know, maybe someone else has a different opinion. So when you, oh, Victoria, I see your question. When we have a tabular data set, the best model to start with is a random forest. So when I have a tabular data set, yeah, so I actually usually start with XGBoost, which is a boosted random forest. XGBoost, like we've probably done 5 or 6 projects like this, and in every case, XGBoost is the best model. And so if you're looking for like specifically what to start with, I usually start with XGBoost. Actually, in a lot of cases, XGBoost does better than neural networks, even on complicated data. Okay, awesome. Keep the questions coming, though. I love it. Okay, so we've already started talking about this a little bit, but I want to go into some detail of how we compare these different models. And so the first concept that I think everybody's going to have some familiarity with is our training and testing splits. So basically, when you have a new data set, you want to split out a certain portion of that data set to be your quote unquote test data set. And you reserve this towards the end, and you use this test data set to evaluate your model. So we're going to train the model on our training data set. And this test data set is only going to be seen at the end, like, for example, when we're publishing the paper. And so then within your training data set, you'll set aside another set, which we call the validation data set. And this is the one that we use to evaluate our models. So like typically how this works is you train the model on you train 5 or 10 different models on your training data set. You pick the model that you like the best based off the performance on this validation data set. And then once you've selected your best model, then you report the results on the test data set in blue. One caveat to this, I think it's becoming more and more common to use multiple test data sets, right? We want to know how our models are going to generalize to unseen patients or different patients. And so, you use your test data set, which was derived from your original samples. But then in a lot of cases, you also include an external test data set that has a different distribution. And so the example I like to give for this, when we were developing our body composition algorithm, we trained the algorithm on quote unquote healthy patients or patients that didn't have a pre-existing condition. But in our publication in the paper, we evaluated the algorithm on patients with HCC liver cancer. And we selected that because these patients tend to have a higher risk of frailty. And we wanted to make sure that the model is going to do a very good job on those frail patients. And so that's an example of this using this second test data set. Okay, so there's a special case of these training and test splits called categorical cross-validation. So this is particularly common with smaller data sets, but I think it can be applied to any size of data set. And so with categorical cross-validation, you set aside a test data set like you would in any other example. But then with your training data set, you basically split your data set into different blocks. And so in this case, I'm showing 4-fold cross-validation. So we split our training data set into 4 blocks. We use one of those blocks for validation and the other 3 for training. And then we rotate which block is our validation block. And so at the end, we're going to have 4 different models that are trained independently 4 different times, but each have seen a different version of the data set. And so the reason this is popular with small data sets is because it allows you to use your entire data set in your training cohort, essentially. So you're not losing, quote unquote, those validation cases. But I think, it's always good to, validate your model multiple times. So I don't think there's any downside to doing cross-validation, even when you have a larger data set. And this example I want to credit. So this is from a project I'm working on with Miko on our team. Okay. So once you have your test data set, your validation, how do we compare the model's performance? And so this goes back to that slide I showed at the very beginning with the blue lines. We need to have a loss function that tells us basically how our model is performing. And as you would expect, there's many different loss functions that we use to evaluate these models. And so I think the most intuitive one is the accuracy. And I should say these are specific for classification tasks. But within classification, the accuracy is just basically the percentage of predictions that you're getting correct. We also break down true positives and false positives as well. And so the term I like to use, basically my degree was in engineering. So I like to call it true positive and false positive. But often people are going to be familiar with this as sensitivity and specificity. And so your true positive rate or your sensitivity is basically the number of positive examples that your model is getting correct. And your specificity or your false negative is the number of positive cases that your model is missing. And so I think the best way to do this is with an interactive example. Oh, just checking the chat here. So I'm going to go back to my spreadsheet for a moment. Okay. So this is the same data set I just showed, but we've added a prediction. So our complication or our ground truth is this green column here. This was on the previous spreadsheet. And we're going to set up this case study where we're trying out 2 different algorithms. And so I have to warn you, I just made these 2 up, but we'll call one of them our logistic regression equation in yellow and the other our random forest in orange. And so for each of these examples, right, we have our true complication. So a 1 if the patient, had some outcome or some complication, and a 0 otherwise. And I've highlighted, the complications as darker just so they're easier to see. And then our model basically is going to output a continuous value. So it'll output some value between 0 and 1, basically on how confident it is that there was a complication. And so we can draw a decision threshold and say that if the model gives us a value below 0.5, then that's a negative or no complication. And if it's above 0.5, then it's positive or yes, there was a complication. And so I've highlighted here the examples that our model thinks are positive. And so one small thing I want to mention here, so the model does output continuous values. And so sometimes we'll call these like probabilities, but it's not actually a probability because the model output is the sigmoid function, right? And so it's forcing our predictions to be usually either 0 or 1. And so the upshot of this is that our model tends to be very, very confident even when it's wrong. So even if the model is not going to be 100% accurate, it's still going to say like 0.9, 0.95, really, really high values. But just for this example, I've kept it a little more continuous. So if we compare our 2 different models, if our logistic regression versus our random forest, you can see that if we were going to broadly generalize here, our logistic regression is getting more of the positives, right? It's getting more of these green ones correct, but it tends to be overanalyzing, right? It's getting false positives here, here, and here. Versus our random forest, which is more specific. So it's not getting all these false positives, but it's also missing 2 of our positive cases. And so, right, if you just look at this data, it's a little bit hard to tell just by looking at it which one is more accurate, right? Because they have very different behavior. So this is where our loss functions come in. So for our 2 examples here, I've summarized the 4 most common metrics that we look at. So the first is accuracy. So you can see that our random forest is doing slightly better. It's getting 88% accurate versus logistic regression. However, the sensitivity is much, much lower. And that's because, it missed those 2 positive examples, whereas our logistic regression got 4 of the 5 positive examples right. And then specificity, our random forest had a higher specificity because it's getting fewer false positive examples. And so even when we look at these table of metrics, it's still not entirely clear, right, which algorithm we like the best. Depending on which metric we use, we're going to choose a different model. And so I think the most powerful tool that we use that hopefully most people have seen before is the ROC curve. And the ROC curve is basically a 2D plot of the specificity versus the sensitivity. And so I won't go into too much detail here, but the ROC curve, so if you had a perfect classifier that was 100% accurate, this relationship would be shown by the green line here. So basically you would have perfect sensitivity regardless of what your specificity value is, because your model's always correct, right? If you have a model that's not telling you anything, if it's just a totally random classifier that's not giving you any useful information, it's going to be this red line here, basically a 1-to-1 relationship. And most models obviously fall somewhere in the middle. So in this case, I've plotted our logistic regression one as orange and our random forest is yellow. And so essentially, the larger the area under this curve, or the closer the curve is to our green line, the better the classifier. And so what you can see is it looks like our random forest in a couple of cases is better than our logistic regression equation. So if we had to make a final decision between these 2 classifiers based on the ROC curve, I would say it's the yellow random forest. And then finally, I want to show in practice what one of these ROC curves looks like. So I stole this example from Pat Johnson on our team. And he's working on a project to classify heart failure, basically, or volume overload from EKG scans, or EKGs. And so this is an ROC curve as it would look like. So you can see that this is actually a really excellent example. The area under the curve is 0.905, which is really, really good for this task. But you can just see what one looks like. Okay, I have a second quiz question, and then I'll open it up for any general questions people have. But this is one actually that happened to me in real life. I came across this in one of my projects, and it took me forever to figure this out, what was going on. And so my question is, if you were to get an ROC curve that's below 0.5, so if you get this yellow curve down here, what is this telling us? Do we have any guesses? You can just say 1, 2, 3, or 4 if you want. One vote for a bug. One vote for 50%. Okay, so we're getting a lot of different guesses here. Yeah, so I'll go ahead and call it. So I'll say Victoria and Bardia are correct. So basically it means that there's an error in your code. And so in the case of like what happened to me, basically I had a negative flipped somewhere in my code. And the reason that is, so like I said before, this red line is the worst possible performance that you can get, right? Nothing can be worse than a random classifier. And so because we are not getting a random value, right? But because we're below this line, it means that our model is still predictive. It's just predicting the wrong thing, which means that our labels are likely flipped. So in this case, I would say that if you get something like this, you should go back and check to make sure that there's no typos. Do we have any other questions on this? So I would say like the ROC curve and the classification examples, this is like really the core of what we do with machine learning. So I want to just make sure that we pause. And does anybody have any questions on this section?
Hi, Alex.
Hey.
So I get really confused, maybe not on model performance, but on data splitting, you know, training, validation, and the test set.
Okay.
I've been reading some articles that they sometimes use cross validation, and then they also, I don't know if I'm wrong, use training and the test set. So I'm just like, it's confusing for me.
Okay, yeah, that's a really good question. Let me go back to this slide. Okay, so when you're doing cross-validation, so first of all, cross-validation is very, very common. So you'll see a lot of papers that are doing cross-validation. When you're using this, you still reserve a test data set, right? So you're still going to set aside test data that's not going to be part of your cross-validation split. And then this fourfold splitting occurs basically on the remainder, so only on the training data set. And so, yeah, so I would say like what you described is how it should be done, right? There should be a test data set and then also reporting results like on the cross-validation folds. Does that make sense? Okay.
And one more question. So, for example, if I say that data test set can act as an external validation, or you will need an extra, like divide the data on an extra, they need to report that. Am I making myself clear?
Yeah, I think so. So you do want to have a test data set that is from your entire or your original data set, right? So when you should have a test data set that's from the same spreadsheet as your training data set. That part is important because you want your test data set to match the distribution of your training data set. But then also, in many cases, you want to have a second external test data set that's from a totally different spreadsheet or a totally different cohort to make sure that your model is going to do very well on new patients. And so I would say, like this first one, having a test data set that's 20% of your split here, this part is essential. And then having an external test data set is optional, but often a really good idea.
Okay, so those are different, like it's not the same.
Yes, and those would be,
Okay.
yeah, correct. Those would be different data sets.
Okay, perfect. Thank you.
Sorry, Alex, I have the same question. Just I'm giving you an example, and I appreciate if you could help me with that.
Okay.
For example, in one article, they said that they divided up all the data set to 80% training data set and validation data set and 20% for test set. And in the same time, they said they used, for example, a threefold cross validation. Okay, can we say they use holdout because they define some percentage for dividing the data set, or they use cross validation?
So I would say they did both. So that 20%, that would be the holdout test data set. And then the cross validation would be the threefolds within the 80%, if that makes sense.
Yeah, I get it. Thank you.
Yeah, so like each cross validation fold then would be like 25%, like 26% of the data, right? Because it's a third of that 80% cohort.
Yes, thank you.
So I will say one of the big limitations here is, for whatever reason, the terminology that people use for these test data sets is very, very different. You know, different papers will call it different things. So the most confusing thing is that sometimes people call this test data set an external validation set. That's their name for it. And they're referring to what I'm calling here as the test data set. And so the same thing, like sometimes people call it a holdout test data set. Sometimes it's just a test data set. And so people use all of these different words for it, basically, and it makes it incredibly confusing. Yeah, for sure. Okay, so I'm going to keep going, but yeah, please keep putting questions in the chat if you have them. Okay, so now I'm going to talk about a few of the strategies that we use that help model performance when you're training. So the weights of the model themselves, like the equations, are called parameters. And then anything that affects the process of training your model, we call hyperparameters, which I know is a very confusing term. But things like the loss function, the learning rate, the number of epochs, batch normalization, these are all examples of hyperparameters. So they're not weights that we're training our model on, they're additional factors that are going to affect the training. So the first thing I want to talk about is this concept of overfitting, which has already come up as we talk about this. And so the simple version of how I like to think about is overfitting occurs when your model is too complicated for your data. And so a lot of the machine learning models are extremely powerful, especially deep neural networks are very, very powerful models. And so they're capable of capturing noise or other random features that are not important. And when it captures these random features, that's going to cause it to make mistakes on new data, because basically it's picking up on variables that are not predictive. And so the diagram that you always see on the internet to illustrate overfitting is, you have the separation between your green dots on top and your orange dots on the bottom. And our model here is, capturing basically every single contour of these dots. If you were to get a new distribution, it's very unlikely that you get a green dot right at this exact location. And so your model is going to make a mistake here. So everybody talks about overfitting in theory. I wanted to give an example of overfitting in practice. So this is actually the same plot that I showed earlier. And this is an example of a model that has some overfitting. And so the way that we read this, so the red curve here is our training loss curve, and our blue is our validation curve. And the reason that there's 4 lines here, so we actually used, this is the same one that we use cross-validation on. So each of these validation curves is from a different cross-validation split. And so how do we know that there's overfitting? So first of all, our training loss is converging on 0. So basically our model has learned the training data set perfectly without making any mistakes. However, if you look at your validation data set, it's slightly higher, right? So it's still converging on a stable value, but it's not 0. It's actually significantly more than 0. And so that means that our model, we would think it would be perfect on the training data set, but on the validation data set, there's this slight gap. And so I don't want to make too much of a negative on overfitting. The truth is all of our models are going to overfit to some extent, right? I don't think I've ever trained a model that didn't have a small amount of overfitting, just because it's natural when you use these really complicated models. The trick is to just minimize this gap as much as you possibly can. Okay, and so, a couple of guidelines or ways I like to think about picking your best model. So like we talked about, sometimes old-fashioned statistics is actually better for tabular data. Sometimes you don't need to go with the most complicated random forest model. You can use something that's simpler. And so cases where this might be important. So if you already know which variables are useful for your clinical task, like for example, with our complications example, if you know that BMI is going to be important, then it could be appropriate to use a model that includes BMI instead of training, a new machine learning algorithm. Another case where you might want a simpler model is where you have a simple data set. So if you suspect that there's only 5 or 10 variables that are going to be important and the rest are probably less important, then you can use a simpler model because you're only capturing a few relationships. And then finally, definitely you should worry about overfitting when you have few samples. And so the rule of thumb that you hear all the time is the 10 times your data set. So you should have 10 times the number of observations as variables. So for example, if you have 10 variables, you should have at least 100 training examples. And of course, there's always a little bit of wiggle room on that, but that's the general guideline. And then finally, if you're not sure which model to use, potentially you can include multiple models together in an ensemble. So this is also something that's very, very common. And so this is an example I'm giving from another project that Miko and I worked on. And essentially we trained 4 different models, and the ROC curves are in gray here. And then we combined all 4 of those into an ensemble by voting. So each model voted basically on each sample, whether or not it's prediction. And then that gives us the blue line here. And so one interesting thing about ensembling I want to point out. So in this example, our ensemble is not actually necessarily the most accurate, right? So in this case, our CV model 2 is doing about the same as our ensemble. But the ensemble is much more consistent. So the CV2 model was not the best one from our validation data set. It actually did quite a bit worse on the validation data set. And so our ensemble is more consistent. So it's less prone to these random errors, basically. It's always going to give us a more consistent prediction. Okay, so I think we are actually coming up on time here. Maybe I'll skip this quiz question. Oh, yes, I want to talk about this. Okay, so I think we got the question earlier of how we can understand what our models are seeing. And so we have a couple of tools that we can use. And probably the most common one that people are familiar with is a feature importance plot. And so feature importance plots basically rank out the variables in your data sets, and they tell you the relative importance relative to the other variables. And so this is an example that I pulled from a project that we're working on with cardiac ultrasound. And so we trained a classifier based on our ultrasound variables to predict whether or not someone has heart disease. And you can see the features that are most important ranked out here. And so the first one is age, second is RA pressure, and then, you know, we have other ones down here as well. So typically you'll see these paired with the ROC curve, right? So on the left, we have ROC curve, which tells us the accuracy or the, you know, performance of our model. And then we'll have a list of variables that are important. And this just helps us understand what the model is doing and double check our work. Okay, so the second tool that we use is SHAP. And SHAP is a Python or an R package, essentially, and it stands for Shapely Additive, I forget what the P is, Shapely Additive Properties, I think. But basically, this is just another tool that we use to explain model performance. So it's very similar to a feature importance plot in how you understand it. But it's a separate code package that basically you run it against your model, and then you know, on your different model outputs, it gives us the importance here in a scatter plot, essentially. So each dot here is one of our test examples or test cases, and then the value is along the y-axis here. And then blue or red indicates whether or not it contributes to a positive prediction in red or a negative prediction in blue. So we can see basically two things. So the strength of the prediction. So if the dots here are farther along the x-axis, that means that this variable is more important. And then it indicates whether or not it's contributing to a positive or negative prediction. And so, you know, this tells us, for example, some of these like reaction timing are less predictive. Things like whether or not they sought medical attention are more predictive. Oh, Shapley additive explanations. Thanks, Puriya and Bardia. That's nice. Okay, so the nice thing about SHAP, so there's two really interesting things about this SHAP technique. So the first is that it works with deep learning models. So the feature importance plots that I showed earlier, they really don't work as well with the deep neural networks, but SHAP does. So it'll, even the most complicated models, you know, SHAP will give you an interesting output for these. And the second thing that I really like is that you can use SHAP with extremely complicated data sets. So this is an example that I presented at Machine Learning Journal Club a few weeks ago, or a couple months ago, basically looking at spectroscopy readings. And so in this case, we have 3,000 different variables that correspond to different compounds in our spectroscopy that are important for prediction. And our SHAP is pulling out a small handful of 5 or 6 of these that are contributing to our prediction. And so, you know, we can parse through all of these thousands of examples and just get a few that are important. And then actually the next stage of this process is we're trying to identify what these compounds are so that we can, you know, use them to inform other research. And I have a link to SHAP down here below. Okay, so I think we are almost out of time. I just want to end with talking about a couple of really practical things of programming languages and packages that we use. So for this one, I called in the cavalry. So I asked basically everyone on our team to tell us what their favorite packages were for doing machine learning research. And so I split these out based on the R and Python programming languages. And so for R, really, there's a really nice set of packages called the tidyverse. And so ones that people are going to be familiar with, probably ggplot, everyone's familiar with who uses R. But, you know, there's a number of here. Stringer is really good for dealing with strings, like text examples. Tidy models, I included a link here. This is the machine learning package. So this is where I would start, like for using random forests and things like that. And then a couple other links as well with R that helps us stay organized. So R Markdown for writing documents, Arsenal, which is a package that was developed here at Mayo Clinic, actually, that automates a lot of the very common statistical analyses that we do. So I think like the R or the ROC curves that I showed earlier were all generated using Arsenal. And then these are more like textbooks or articles, but there's some additional resources that this R for Data Science especially is a really nice textbook if anybody's interested in this. And then finally, the Python packages. So, I mean, there are hundreds of different Python packages that'll do this. So I'm sure that your favorite package is probably missing from my list, but just a couple of ones that I use. So Pandas, I would say, is essential for cleaning up data sets and for data visualization. I really like sklearn for machine learning. Fuzzy Wuzzy is a really nice package for natural language processing that helps actually, this is what Heather used in that example for parsing through the text files. And then if you're at the point where you're thinking about model deployment, weights and biases is a really nice way to track your training and keep track of hyperparameters. And then finally, I think most people are familiar with the deep learning frameworks for Python. So TensorFlow versus PyTorch. The biggest difference with these is for those of us who are using Google Cloud Platform, TensorFlow is actually a Google offering, right? It was developed by Google, and so it's a little bit more compatible with cloud than potentially PyTorch can be. On Google Cloud, I should say. And then the last one I want to mention is H2O, which is an AutoML tool. So it'll do, it's basically available in Python or R. And it'll do your modeling for you, basically. So it'll step through a number of different models, including random forest, SVMs, logistic regression, and then it'll do your hyperparameter tuning as well. Okay, so I think we are out of time. So I have a couple of slides here on project management, essentially, but I think I'm going to pause at this point because I want to save just the last couple minutes for any questions.
Thank you, Alex. I wanted to ask you a question regarding, you said that these models are very sophisticated and can handle a number of variables, and including if you have in mind the number of variable to outcome ratio of 10 or something like that. But what about feature selection? So is it, for example, a good idea to select the most relevant features using another model or from prior knowledge, and only feed those selected features to your ML model?
Yeah, that's a great question. So I think it can go both ways. So actually, we've done both techniques for different projects that I've worked on. And so sometimes you can train. So we've actually done where you use a machine learning model for feature selection and then train an entirely different model on basically the features that you've selected. So it's like a two-step process. You do your feature selection and then you train your model. That's fine. A lot of the machine learning algorithms are self-regularizing, essentially, right? So if your machine learning model is trained properly, it should know to ignore variables that are not important. And so you don't always need to do that feature selection step. I think it really comes down to which model you're using and what your data set looks like.
Thanks a lot.
Yeah, thanks. Okay, so I see the question in the chat about other training or resources. So I have a lot of links in this presentation. So if you just email me after, I can share the PowerPoint with you and you can go through all these links. So I have textbooks for both R and Python and short articles as well that could be helpful. So actually with that, I'll skip ahead. So I think everybody here at Mayo has my contact information, but if not, here's my email.
Thank you, Alex. Thank you, Purya, for keeping track of the questions in the chat box. And we have 2 other workshops coming up. We hope to see you there.
Thank you very much. Thanks everyone for coming.